Greeting, guys. We've reached the Cauchy Euler equation part of our Module 2 lectures. We've already talked about constant coefficient differential equations, which is the predominant part of Module 2. We started with an introduction to these equations. We introduced you guys to reduction of order method, where if you've been given a second order differential equation with constant coefficients and one of the solutions, you can always find the second solution using the formula I provided for you, and that formula could be derived. We moved on to calculating the characteristic equation, figuring it out, finding its roots, and writing the solutions to constant coefficient homogeneous differential equations based on those roots. We then introduced you to two methods of solving non-homogeneous differential equations that are constant coefficients, and there were undetermined coefficients and variation of parameters. And that concludes the part of the module on working with solving constant coefficient differential equations. Now, the second part of our task will be to look at differential equations that do not have constant coefficients. That's Module 3. And that's when you'll have power series solutions. However, there is a particular type of a differential equation that has non-constant coefficients that could still be solved without using power series and basically using another version of a characteristic equation. Now, that happens when your differential equation that has non-constant coefficients has coefficients where the power of that polynomial or the coefficient matches the order of the differential equation. For example, I could have been writing a differential equation such as 3x squared y double prime minus 5x y prime plus 6y equal to 0. This is a non-constant differential equation, coefficient differential equation. However, the power of the coefficient, which is 2, matches the order of the derivative. But power of the coefficient, which is 1, matches the order of the derivative. The power of the coefficient, which is 0, matches the order of the derivative since there are no derivatives. When that happens, we could basically somehow guess at a fundamental solution, and then based on that solution actually come up with a characteristic equation and then write the different types of solutions based on the nature of the roots of that characteristic equation, just like the case for the constant coefficient version of this differential equation. Now, Cauchy Euler were the ones that came up with this concept and saw it, so therefore these are called Cauchy Euler equations. So any non-constant coefficient differential equation where the power of the constant matches the order of the derivative, as I've shown you here, could be solved with making the fundamental guess on the solution of being y is equal to x to some power of n. This is the fundamental guess for Cauchy Euler equations. And if you take the appropriate derivatives of this fundamental solution and plug it into the given differential equation, and I'm going to take a second order as an example, you will end up with the following characteristic equation: am squared plus b minus am plus c equal to 0. And basically, based on the roots of that solution, the solution to this quadratic equation, then you could write your homogeneous solution for your Cauchy Euler equation. Now, let me give you the cases here and I'm going to do this for a second order, but if it's a third, fourth, or fifth order, you could always start with this equation, take derivatives, plug it in, and end up with your own characteristic equation for that particular differential equation. Again, I'm giving you the case for a second order differential equation so that you could actually write the solutions based on what I'm telling you and then extend it if you have a higher order differential equations. Now, if the characteristic equation for the Cauchy Euler gives you distinct real roots, I'm going to call it case 1. So you're going to solve a second order differential equation, the characteristic equation for it, and you're going to get distinct real roots. So you're going to get distinct real roots. So your roots are going to be m1 and m2, and they're going to be distinct and real. And therefore, at this point, your homogeneous solution for Cauchy Euler equation will be C1 instead of e to the power of, which was the solution for the constant coefficient case. Here, it will just be a polynomial x to the power of the first root plus C2 x to the power of the second root. Now, if you had a third order, fourth order, fifth order, and you had more distinct roots, you'll just continue writing plus C3x to the M3 plus C4x to the M4, and so on. My second case will be repeated real roots. Again, just like the counterpart in the constant coefficient differential equation case, with slightly different modification here, your homogeneous solution will be C1x to the M1 plus C2. Now, in the case of the exponential, the constant coefficient here, it would have been C2x e to the something. But in the case of Cauchy Euler, it will be C2 ln of x and then x to the power of M1. So here, instead of x, I'm incorporating natural log of x. Just that's how the cookie crumbles, as per they say. Now, ultimately, if I have complex conjugate pairs as my solution, so that'll be case 3. So here I have complex conjugate roots. So my roots are M1 will be alpha plus beta I, and my M2 will be alpha minus beta I. And now, if that's my solution to the characteristic equation, my homogeneous solution will then be written as x to the power of alpha. Remember, it was e to the power of alpha x, but here, for the Cauchy Euler, it will just be a polynomial, so there'll be no exponential, so it'll just be x to the power of alpha. And it'll be C1 cosine of, and then you'll use the coefficient of the imaginary part, beta, and then you'll have ln of x, and that'll be your argument, cosine of beta ln of x plus C2 sine of beta ln of x. And this will be the case where you have complex conjugate pairs. I'm going to give you guys 3 examples for these 3 cases, and then I will leave it up to you to start doing more exercises with the rest of the homework assignments. So let's look at an example here. The first one I want to look at, again, they have to be Cauchy Euler, so it'll be x squared, say y double prime, minus 2x y prime, minus 4y equal to 0. Now, if I write the characteristic equation here, I'll have m squared minus 3m minus 4 equal to 0. You should be able to derive this characteristic equation by assuming your fundamental solution to be x to the m and taking the appropriate derivatives of this. And plugging it into the differential equation and coming up with that characteristic equation. You should do this at least once or twice to see how you could derive these if you don't want to memorize them. Then you will solve this quadratic equation. You'll get 2 roots. M1 is minus 1 and M2 is 4. And since I have distinct real roots, then I could simply write the solution as, since it's a homogeneous one, I could write the solution as C1x to the power of the first root plus C2x to the power of the second root. And that becomes my homogeneous solution if I have distinct real roots. I'm going to go to the second case. So I'm going to give you another example. Now let's say my differential equation is 4x squared y double prime plus 8x y prime plus y equal to 0. I'll write my characteristic equation for these Cauchy Euler equations. Of course, it is, again, just one more time, if you notice, to remind you, 2, 2, 1, 1, 0, 0. So it is a Cauchy Euler. So I can write my characteristic equation, and it will be 4m squared plus 4m plus 1 equal to 0. And you notice here I will have a double root. M1 is equal to M2 is equal to minus 1/2 as my double root. So this is the case where I have repeated roots. So I could write my solution, homogeneous solution to Cauchy Euler as C1x to the power of the root, which is minus 1/2, plus, that's right, C2. Now I'm not going to put x, I have to put ln of x, so it'll be C2 ln of x times x to the power of minus 1/2. And that becomes my homogeneous solution. So I'm going to put this in a box. And that becomes my homogeneous solution for the repeated root case. And now we'll move on to our third example. I have 4x squared, let's see, y double prime plus 17y equals 0. And let's see how we can go about solving this one. Now, if I were to write the characteristic equation for this, I'll have 4m squared minus 4m plus 17 equal to 0. If I solve this quadratic equation, I'll get my complex conjugate pairs as 1/2 plus or minus 2i. So those are my m1 and m2. So now I can write this homogeneous solution as x to the power of the real part of my complex conjugate pairs. So x to the power of 1/2. And then this becomes C1 cosine of 2 ln of x. The 2 comes from the coefficient, the complex part of my, the imaginary part of my complex number. And the ln of x is just existing. And that will be my argument for my cosine. And then it will be plus C2 sine of this time 2 ln of x. And that will be my homogeneous solution for complex conjugate pairs. And let me be consistent. Put this in the yellow box as well. And here's my solution when I have complex conjugate pairs for Cauchy Euler equations. So now it's time for you guys to do some practices with these equations.